Okay, hi, this is my video number 12. My video number 12. Right. So I'll talk on the derivative and integral. Excuse me. I'll talk on the derivative and integral of vector function. Derivative and integral of vector function. Okay, so let me give you first a definition on the what integral means. So we have a definition that vector function Rt with component ft, gt and ht, then dr dt is given as limit delta t approaches 0 r t plus delta t minus rt over delta t. Yeah, if you remember the definition of differentiation for the real valued function, there's some similar. We have instead of vector function, we have a real valued function. Normally we use h here, and h approaches 0. Now in this case, because r is, we can consider as a moving object from one point to another point, where for each or at each point on the curve can be represented as a position vector rt. So it's depend on t. So we differentiate with respect to t. Now, how can we look at this? How can we describe this thing in figure? Right. So if we consider in three-dimensional, and we have a, let's say, the curve, the vector, the curve, and at point P, say, and at point Q on the curve, and at point P we have a position vector RT. That. So this is RT, and after some points, or sometimes, this is might difficult for me to see, so let me draw other photo, other figure. So let's say I have that, so much easier for me because we want to draw the second line. So let's say at certain point P, we have a position vector here. This is our RT. Okay, and after some times, those object move up to Q. So let's say this position vector. So after some times, let's say after after delta t time. Okay, so we have Rn RT plus delta t here. So if you consider the second line PQ, second line which connect P and Q, so we have that. Okay, consider this as a vector from P to Q. So this vector from P to Q basically is R t plus delta t minus RT. Yeah, that vector here. So it's formed, this vector PQ formed from two position vector OP and OQ, where O is here. So as we can see here, as delta t approaches 0, what does it mean delta t approaches 0? Yeah, what does it mean? So if you make it delta t as getting smaller and smaller, so which means it just move from PQ, the point Q approaches P. Yeah, the point Q approaches C. So what happened if Q is here? So look carefully. So if Q is here, there, so we have the tangent. The second line becomes, this is our second line. That. So if Q getting closer to P, so we have a second line there, and then later on when it is close enough to P, so we have just a line touching a point P. So that gives you a tangent line. So what happened now, as delta t approaches 0, the second line goes to tangent line. Tangent line, not good. Pen is not good. Okay, so what we have is that as delta t approaches 0, now we have r prime, because as delta t approaches 0 here, so r close enough to rt close enough to r, and delta t approaches 0, so we have that give you dr dt. So dr dt, I can denote that as a r prime as dr dt. Yeah, so this give us a tangent vector, to the curve, defined by r, at point P. So if I can sketch again, those things just look like in 3 dimension. If you have let's say our point P is here, so r prime is what we got is the tangent line at point P. Yeah, tangent line at point P. So if this is r, then this is our r prime. So this is r, that's our r prime. Okay, and for the vector unit tangent, so means this vector unit tangent. So for vector unit tangent, that perpendicular to r. So we have we denote that as t. This is given as r prime over t over magnitude of r prime over t. Yeah, vector unit tangent. Okay, now let's look at a theorem on differentiable function. If a vector function r, with component f, t, gt, and ht, where f, g, and h, where f, g, and h are differentiable, then differentiable function, then r prime t is given as we differentiate each of those components, t, g prime t, and h prime t. So to prove this theorem, we just use the definition of derivative. Yeah, we use the definition of derivative. So what the definition of derivative? We have r prime is given as limit delta t approaches 0. Yeah, rt plus delta t minus rt minus over delta t. So we use that definition. Okay, so proof. Now from the definition we have r prime t, this is a limit delta t approaches 0. So we have r t plus delta t minus r t over delta t. So we can substitute instead of rt here now r delta t plus delta t. So what we have, so I might need more space here, I put it here. So limit delta t approaches 0. So we have r t plus delta t. So in terms of component, so we have f. I can take out delta t here. So take out those things, delta t. So now what we have is f t plus delta t, g t plus delta t, h t plus delta t. Okay, that's a vector. Oh, you need those bracket there. Minus rt. So our rt is with the component ft, gt, and ht. Okay, so you can rearrange those things. That gives us the limit delta t approaches 0. So we have f t plus delta t minus ft. That's the first component. We subtract component by component over delta t. So we have g t plus delta t minus gt over delta t, and we have, I write it here for the third component, h t plus delta t minus ht over delta t. Of course, in terms of limit, we can put the limit inside. So put the limit inside for each of these components. So what we have, I just rewrite this thing. So in terms of, we take a limit for each of those components, delta t to 0, f t plus delta t minus ft over delta t. That the first component. Second component, we can do the same. Limit delta t approaches 0. We have g t plus delta t minus gt over delta t. And for the third component, we take a limit delta t approaches 0, h t plus delta t minus ht over delta t. Okay, so this is nothing different than the definition of the derivative for the real value function, because f, g, h is differentiable and real value function, so which means this limit exists, this limit exists, all those limits exist. So this is the definition, basically definition for the real value function. So we have, then we have, this is just f prime t, this is g prime t, this is h prime t. Okay, yeah, of course I have a example for that, but it's simple. Yeah, just a simple example, just to show you how to apply the derivative for the vector function. Yeah. Okay, let's consider, doesn't it? Doesn't matter, even it is simple. Right? If you have example, if you have a vector function given as set of t 2 minus t, yeah, just 2 dimension, right? Now find r prime t and sketch r1 and r prime 1. Now remember that this is the representation of for the vector. Yeah, I've mentioned you many times, especially at the beginning of our lectures. Of course, this can be written as in terms of ijk. You can write this as I plus 2 minus dj. Yeah, I don't want you to get confused. Yeah, sometimes we use this. If you find a book, sometimes we use this, sometimes we use that. And even some book use just a simple curve brackets. Yeah, but remember that this is a vector. Now in this class, I don't want you to use curve because we use just handwriting, so we cannot make it bold. Yeah, so make sure always differentiate between vector and points. Curve bracket we use for points. This sharp bracket we use for the for vector. Now for this example, so it's easy for you to differentiate those things. Yeah. Solution. So to differentiate those, we just differentiate each of those. So this gives you we have a 1 over 2 square root t. That one we have minus 1. Okay, and then we evaluate because we want to evaluate. So now we find that one. Okay, now we want to evaluate what is R1, what is R prime 1. Okay, if you evaluate those things, so R1 that give you so we have we sketch R1, so this give you 1 1, so we have 1 1. Okay, and R prime 1, this is 1 over 2 minus 1. 1 over 2 minus 1. Now how to sketch this? Yeah, how to sketch? So if you look at those component of vector function r, here you can consider component in x in x direction or y direction, this component in y direction. So I can write those as x equal to set t and y equal to 2 minus t. So we can do this. So from here, so you can write, of course from that you can write as a t is x squared. Correct? Therefore, we have y is equal to 2 minus x squared. So from here, at once you can recognize what kind of curve is this. Okay? So I can plot this much easier rather than you find the point for each of those. So if you look at this, then you can basically you recognize this. So we have a curve. I would say like a cup upside down, cross the y-axis at y equal to 2. Alright, so we have 2 is here, and cross x-axis as square root, x-axis as square root plus minus 2. So square root plus minus square root of 2. So maybe let's make it here, for example. And if you look at the, of course you can sketch those. This is your RT. Oh, should touch that. Okay, that's your RT. Okay, now to sketch those vector R1, so R1 given as 1 1. Yeah, so 1 1 means if you write this in terms of ijk, so we have 1 I plus j. What does it mean? So it means 1 to the I. So because we have only one, the coefficient in front is just 1. Here is always 1. So which means we have from 0 here, okay, because this vector position, so 1, so move 1 to the right, okay, and move 1 to the to top, okay, that. And the position vector at 0, 0, so we have those vector like, should touch, okay, let put that point here. So that's the vector. So this is our RT at point, sorry, so this is R1, sorry, R1. And R prime 1 1, yeah, R prime 1 1 given as so we have half to the right, so begin from there, half to the right, and then minus 1 going down, so let's say somewhere here up to that point, yeah. So therefore our point is, the vector is that. This is our vector. That's our R prime 1. Okay. Oh. Okay, then next, okay, give you another example. Find the parametric equation for the tangent line. Find the symmetry equation for the tangent line to the helix with parametric equation to the helix with parametric equation given as x 2 cos t y sin t and z equal to t at, say, points, let's give a name here, P, say point P, 0, 1, pi over 2. Okay, so if you write this in terms of vector, so you can write this, the vector position for that, as your RT is given as component of, for x is 2 cos t, component for y is sin t, and component for z is t. And then if you differentiate this, r prime t, that gives you minus 2 sin t, cos t, and 1. And if you differentiate evaluate r prime, evaluate r prime at pi over 2, why I choose, okay, let me choose z equal to t, because if you choose x or y, okay, if you substitute x here, you need to substitute x 0, then you can find t. Here you need to substitute y equal to 1, you need equal to 1 in order for you to find t. For this case, you just put z pi over 2, then you can find t directly. So that's why I choose z equal to 2 as a reference point, our reference point. So if you substitute this or evaluate r prime at pi over 2, that gives us sine pi over 2 is 1, so we got minus 2. Then for cos pi over 2, that's 0 and 1. So we need to find the symmetric equation for the tangent line. So which means this is a straight line. Okay, a straight line, but instead of a vector equation, we need symmetric equation. So you know what symmetric equation is: x minus x naught divided by t, z minus z naught, and so on. X minus x naught divide x naught equal to y minus x, y naught over y naught, and so on, so on. Now, for the straight line, the equation of the straight line, just let me recall that what we have learned. So if this is the line that we want to find, the equation, the line of the equation, the equation of line that we want to find, then we need a vector that parallel to that line, and at least one point, let's call, on that line. So we have let's say x naught, y naught, z naught. So v with v1, v2, v3. Yeah, so this vector parallel to the line. So now by having this, so which means this vector r prime here parallel to what we are looking for. You have a line, you have a curve. Let's say you have a curve like this. Okay, when t equal to pi over 2, maybe somewhere here. So this is your r at pi over 2, and then r prime is we have a tangent touching that point, that. So this is the one that we're looking for. So the vector that parallel to that line is given as a differentiation of r. So that's why we have those things. So therefore the parametric equation, we're looking for a parameter. Sorry, this should be parametric equation, not symmetric equation. Parametric equation. Yeah. So now you have that. You also have point. Your point is given here. So which means our point P, x naught, y naught, z naught here is 0, 1, and pi over 2. So therefore, the equation of a tangent line, we have x equal to x naught. Our x naught is 0 plus our v is that. So we have minus 2 t y equal to 1 plus 0t, and our z is equal to pi over 2 plus t. Okay, just rewrite those things in the proper manner. So we have x equal to minus 2t, y equal to 1, and z equal to pi over 2 plus 1. So that gives you the parametric equation of the tangent line. Okay, if you can do the first derivative for a given vector function, if we were given vector function, let's say r equal to rt, now we have shown that we can find what is r prime is defined as that, which is dr over dt. Also we can find r double prime. Yeah, r double prime, which means we differentiate with respect to t twice. So we have d 2r over dt2. and so on and so forth. We can keep on differentiate as long as the function is smooth, continuous, and everything. So you can always differentiate those as much as many times as you want. Now we have the definition. If we have a function that we can always differentiate as many times as we want, and it can give you some result, which means the function is always continuous and continuous for each time we derive, each time we differentiate. So those function we call it as a smooth function. Okay, so a curve R, this is R as a vector function, represented a curve. So this curve is called smooth. Get the word there, smooth. On some interval I, say, if R double prime T is continuous, and R prime T different than 0, except possibly at the endpoint. Except possibly at any endpoint. Any endpoint of I. Now, example. Verify that the curve given by L, x equal to t minus 1 squared, y equal to t cubed, and z equal to t, where t from 0 to 4 is smooth. So it is of course not difficult to show the smoothness of this given function or curve. Okay, you can write that as a vector function, or you can directly integrate each of those components of this vector function, then show that this function are continuous. So if you can write this as a vector function, so what we have, R is equal to, we have xt, yt, zt. So each of those we have t minus 1 squared, t cubed, and t. So if we find R prime, that gives us 2t minus 1, we have 3t squared, and we have 0. Of course, this is just a linear function. This is your x prime, this is your y prime, this is your z prime. This is a linear function, this is quadratic function, this is just a constant function, which means x prime, y prime, and z prime are continuous. So in this case, we have x prime, y prime, and z prime are continuous. Therefore, R prime is also continuous. So therefore, R is smooth function, or the curve itself, L, is a smooth curve. Okay. The question is, are all functions smooth? Of course not. If you remember, when we consider for the real value function, you have a modulus function, for example. Okay, if you consider modulus function, y equal to x, Yeah, if you plot that graph for that function, so you have this kind of function, right? That. So graphically we can see that the function is not smooth here. Not smooth means when you plot the graph, then we change the direction of those suddenly. So you can see the changes there is very sharp. So we have very sharp corner here. So it means it's not smooth. So for this function, it is continuous. Yeah, it is continuous. Y itself is continuous. But what about y prime? Does it also continuous? There's question mark. I believe you have gone through this. I'm not interested to repeat that again, but just to give you an idea that because the vector function is formed from the real value function as a components for x and y and z, and if each of those components, which is the real value function, continuous, then of course our vector function is also continuous. So think of those things, and let me give you some a simple exercise. Some simple exercise is this curve x equal to t minus 1, y equal to t squared, okay, z equal to 1 over t. Yeah, for t 0 and 2. Of course you can include 2 if you want, no problem. Is this curve smooth? So I leave this as an exercise. Maybe you can submit this question to me, because I think a day or before yesterday someone asked me about the quiz. So I put this question as a quiz to you. Yeah, as a quiz one. I will set up the in the Putra Blast that you can submit those things. Okay, so I give you so our class is at 4:05, so you can submit before 5:15 this afternoon. Okay. Of course, I have some example. Yeah, I think enough for the smoothness of the function. Now let's see some rule for the derivative. The differentiation rule. So we have d dt ut plus vt. This is rule number 1. Oh, sorry, I should have some wording there. So theorem, suppose u and v are differentiable vector function, differentiable vector function. I just put that up. Vf as a vector function, and C in R scalar, and F is a real valued function, a real valued function. Then we have couple of rules. dt of c ut, this is given as c u prime t. Number 2, we have ddt u plus ut, of course, vt, this is u prime t plus v prime t. Number 3, we have ddt f ut. So in this case, we have the multiplication of real value and vector value function. So this is f prime tut plus ft u prime t. Number 4, we have ddt. We differentiate the multiplication of two vector function ut dot vt, that give us u prime t dot vt plus ut dot v prime t. So do not forget the operation dot here, because if you just write uv like this, it's meaningless, because as a vector you need some operation, there, either dot product or cross product. So you cannot simply write uv just like that, when we write the real valued function. There is difference. So that's why if you look at here, we always have this dot and dot, as compared to this one, because f is a real valued function, then we can write as a normal multiplication. But in the case of a vector function, you cannot do it. That's 4 and 5. We have ddt u t times vt. This is for cross product. This is u prime t cross vt plus ut times v prime t. So basically what we do when you differentiate is that we fix one of them, differentiate that, plus fix another one, and then differentiate those things. It's just basically similar to or identical to a real valued function. And number 6, we have ddt u function of ft, here composite function. This is f prime t u prime ft. So this is a basically chain rule for the vector function. Chain rule. Okay, for the proof, what we need to do is just consider those vector uv with components, let's say f1, f2, f3, this one let's say g1, g2, g3, and then perform product, and then it will give you the real valued function. Then you can perform the derivative as required. So let me give you proof to one of these. I want to I select the easiest one, I would say. Yeah. So let's say I prove which one? Number 4. Okay, proof of 4. Property number 4. So others you can do it as an exercise. Okay, let's u as a function of f1t, f2t, f3t, and v is a function of g1t, g2t, and g3t. Then u dot v is given as, we dot product between those two vectors, means we multiply each component of each of those vectors, right? So we have f1 g1 plus f2 g2 plus f3 g3. Of course, this is a function of t, or in short, of course, you can write this as a fi gi. You can write this thing, summation I from 1 to 3. So then if you differentiate this respect to t, so d dt u dot v, so which means we differentiate those d dt sum fi gi, fg component of vector of t. So of course you can write this as a summation I to 3 d dt fi gi. In this case, we differentiate the real valued function, so we can just use the properties of the differentiation rule for the real valued function. So that will give you I from 1 to 3. This we have fi prime of t g I t plus f of t fi g prime gi prime t. Okay, so this is nothing more than the u prime of t dot vt plus u t dot v prime t. Okay, I can give you another simple example. Show that if the magnitude of R is C, a constant. Okay, so show that if R is given, magnitude of R is given as C, then R prime T is orthogonal to RT for all T. So how to do this? Solution. Given that I can write this squared as a t squared. This is R squared. This is R of t dot R of t. That give you those. Okay, so if you differentiate both sides, so what we have on the left side, we have using the definition or the rule that I gave earlier. So this is R prime t dot RT plus RT dot r prime t. Yeah, and we differentiate on the right side. This is just a constant. We differentiate respect t, give you 0. So from there we have 2 r prime dot rt that gives 0. So therefore r prime t dot rt that 0. So this statement means that r prime always perpendicular to r for all t. Okay, so I think with those I gave what I have explained to you what is the let me recall those things. I gave you the definition of derivative for the vector function. I explained you what does it mean for the limit of delta t approaches 0, and also give you a couple of example, and also the rule for the derivative. Yeah, and don't forget at the end of this we have a quiz. Yeah, and submit before I give you 5 minutes to solve this problem, and plus minus yeah, 5:15 you should submit those things as okay. Bye bye.